In this video, I will talk about computing the area of a certain object, in particular the area under a curve, like shown here on the right graph. But let me start with some areas first. So here I show you 4 areas which need to be computed. A rectangle is easy, right? It is length times width, so we can do this. A triangle is also easy. It is 1/2 base times height, which is good. And then here the area is just A1 plus A2 plus A3 plus A4, so we can do that too. But the big question is, here we have a curve f of x, and we would like to know the area under the curve of f between the values a and b. Now this is maybe not so clear, but this could be. This is what this video and also the following videos are about, is how to compute an area under a curve. Here I just give you the basic idea, but the real mathematics will be done in one of the subsequent videos. So the area under a curve is actually quite important in many applications. For example, if you want to know the area of a leaf for photosynthesis, or you're interested in the size of a tumor if you see an MRI image and you wouldn't need to estimate the size of the tumor. You could be interested in the total uptake of fertilizer in a field of crop. How much fertilizer did you use and how much do you still have to use? Or similar, the uptake of a drug from a patient. So if you know what your injection is of the drug, you might also need to know what the total amount of drug is which was administered to a given patient. You could be interested in organ sizes or capacities, for example, capacity of the lung. Or on a micro scale, you're certainly interested in cell surface areas, because the cell surface area is proportional to the reactivity of a cell or its sensitivity to signaling pathways, etc. So here's the area problem again. So this is an area, the blue shaded area S, I like to compute. So I would like to approximate it with areas of objects which I know very well. And for example, what I know very well are rectangles. So why don't I just put a rectangle, say here, and use the rectangle to approximate the area inside this rectangle. And then I use a neighboring rectangle and another neighboring rectangle, and maybe fill the whole area I'm interested in with these rectangles. And then I hope, actually, as it looks like I will, get a pretty good approximation of S. So the idea is the following. So the area under the curve, which we call S, I would like to approximate. I approximate this by using rectangles. And now let us start with a specific example of f of x is equal to x squared, just the normal parabola. And I would like to do this construction with the rectangles. I divide the interval from 0 to 1 into 4 subintervals. And then I look at the function value on those points. I go up to the function here. And then I use these points to build my rectangles. So maybe these points are the right points of a rectangle. So then I complete the rectangle like this. And here I build a rectangle like this, and here like this, and here with the endpoint like this. And then I get sub-areas A1, A2, A3, and A4. And then I call this R4. R stands now for the right-sided point, so the right-sided point is on the curve. So R4 I define as A1 plus A2 plus A3 plus A4. And then I hope that this might be a good approximation of the area I'm interested in. Well, you might say, of course, it is not a good approximation, right? Because I'm making mistakes here. So here I make errors, I count too much. But maybe these errors go away if I make more and more rectangles and finer grids along the x-axis. So let's for now keep this with 4 subintervals, 4 sub-areas A1 to A4, and let's call this R4. I can do it the other way also. Again, I use the same 4 points along the curve, but now I use these points to be the left endpoints of the interval which builds my rectangle. So that's the left endpoint, I make a rectangle like this. Here I make a rectangle like this, and here like this. So let's call this B4, B3, B2. Actually, B1 is not really present because there's no height. And then I call L4 to be the area B1 plus B2 plus B3 plus B4. Again, I'm making a mistake because there are bits of pieces of the area which I'm missing. But let's not worry about this for now. Maybe it goes away. So R stands for the right endpoint of an interval is on the curve, L stands for the left endpoint is on the curve. Let's compute this actually. Let's see what values we get. So here I do the same thing, but now I have these intervals 0 to 1/4, 1/2, 3/4, and 1. And so then these are my little areas, A1, A2, A3, A4, and then I can compute. So R4 is A1 plus A2 plus A3 plus A4, and so A1 has, the baseline is 1/4, and the height is the function x square evaluated at 1/4. I just write this as 1/4 square. The next interval has again the base length 1/4, but then the height here is 1/2 square. And then the next one is 1/4 times 3/4 square. And then we have A4, which is 1/4 baseline times the height 1 squared. So multiply all this out, you get 1532, which is 0.468. But also we know that the area we are interested in, which we called S, is certainly less than R4, because we made a whole bunch of mistakes here and here, so we counted too much. We counted too much area. But don't worry about this, this might disappear. Let's do it the other way. So L4 was B1 plus B2 plus B3 plus B4. So this is B3, this is B4, this is B2. B1 is empty, so this is 0. But B2 has the base length 1/4 and the height 1/4 square plus 1/4 1/2 square plus 1/4 3/4 square. Okay? And then this is computed to be 7/32, which is 0.218. This number is quite a bit smaller than R4 was. And of course we know as well that L4 in this case is less than the area we are interested in, because we are missing bits and bits and bits here and here and here. What happens if we make this finer and finer? Let's do that here. So now I look at the right-sided intervals where the right point of the rectangle sits on the curve, and here I use 10 rectangles, here I use 30, and here I use 50. And so you see the approximation to the curve, or actually to the area S, becomes better and better. And while I'm making an error here, the error is smaller here and even smaller in this one. So as n goes to infinity, I can actually hope that the error goes to 0. How about in the other case when I use the left endpoints? So then I'm missing bits here and here. So here I use 10, here I use 30, and I use 50. And then again, the pieces which I'm missing, they kind of disappear. And again, in the limit, I have the hope that this might actually work. Let's look at this numerically also. So here I increase from 10 to 20 to 30 to 1000. And then I compute the left-sided rule for the rectangles and the right-sided rule for the rectangles. And you see at 1000 they get very, very close. They're at 0.3328 and 0.3338. It even looks like they converge to 1/3. Well, that's indeed the case. So what we will see later is S is equal to the limit as n goes to infinity of the ln's. And then this is actually the same limit as n goes to infinity of the rn's. And then it turns out this will be 1/3. We will learn method how to do this much more efficiently than using these rectangles, but the rectangles are more like a motivation to get this whole idea started. Now it is interesting that we can actually use general sample points. So we do not have to use the left endpoint to be on the curve or the right endpoint of a rectangle being on a curve. We can have any point of the rectangle touching the curve. So let me show this here in this graph. So for example, this point x1 star actually sits a little bit off the left boundary, right? It's to the left, but it is not the left endpoint. x2 star, for example, has been chosen pretty much in the middle of the rectangle. x3 star is a little bit more to the right, but it is not the right endpoint, etc., etc. So more in the middle, more in the middle, more in the middle, and here a little bit more to the right. And so then if we call these subintervals, let's call this A1 and this A2 and this A3. So then the size of A1 will be this guy. This is the height, f of x1 star, times delta x, which is the distance on the x-axis. And then this guy will be A2, etc., etc., and this guy will be AN, so the last subinterval. And this works too. So it doesn't really matter which kind of points we use. If it's the left endpoint of a rectangle or the right endpoint of a rectangle or something in between, it all works. And then this is called the area, or actually we called it S earlier. Let me summarize. So we saw that the area under a curve can be approximated by using rectangles. However, we also saw that we have to make the spacing of the rectangles very, very small to get a very good approximation. We saw that the choice of sample points is not so important. In the limit, as the spacing becomes finer and finer, the sample point does not matter. After watching this video, you should be able to compute R4 or L4. Remember, R4 uses the right endpoint on the curve, L4 uses the left point on the curve for simple functions, meaning like 1 plus x squared or something very simple. Well, as well as a few higher ones, so maybe 3, 4, 5, 6, 7, 8, up to 10, and L3 up to L10. And you will get ample opportunity to practice those in class and in the homework problems. Oh, hi, Tolo. What are you doing? Having a good time?